Okay, first one. When it comes to alkanes, everybody, what are the basic terms that we must know? Check it out. If C1 to C4 we have, C1 to C4, all the forms of alkanes are gaseous in nature. C5 to C17, they are liquids in nature. And C18 and greater, they are waxy solids in nature. Waxy solids. Okay. Just from Dezine to Vaseline to, grease, everything, those are all, waxy solids. Next, boiling point and melting point, if you compare, as the molar mass of the alkanes increases, the boiling point always increases because the van der Waals forces of attraction increases as the molar mass usually increases. Now, if at all I talk about the isomeric part, for instance, if I take pentane, okay, like this is N-pentane, okay, and if I compare this N-pentane with uh, uh, 2-methyl butane, this is methyl butane, methyl butane. While if I compare that with, you know, dimethyl propane, dimethyl propane. If you compare this, as the branching increases, the boiling point will always decrease. So keep that in mind. So boiling point generally is inversely proportional to branching of the groups. Okay, next. As it comes to melting point, it is slightly different. Usually we expect that melting point should also increase as the mass increases. Okay, so we generally expect pentane to be greater than butane. But as it comes to propane, methane, and ethane, there is some exception. Ethane will slightly have better. Usually, what happens is even number of carbons will always have a better arrangement of molecules as compared to odd number of hydrocarbons. So, therefore, ethane would have a better ability of stacking itself compared to methane and propane. Hence, the melting point. So, generally, even is greater than odd. Okay. Next, heat of combustion. Heat of combustion for alkanes mainly depends upon number of carbons. More the number of carbons, more is the heat of combustion. It doesn't matter whether it has branches or not. You will first priority is always about number of carbons. Next, in case of isomeric alkanes, if you have, you need to check out heat of combustion on the basis of number of branches. Okay. Now, if you have pentane, then you have isopentane, then we have neopentane here. If you compare these three, then more the branching, less will be the heat of combustion. Got it? So these are few important physical characteristics that you should know about alkenes. Now, what are the chemical properties of alkenes? You can notice that usually alkenes do not make a lot of reactions, but as it comes to reactions, it will definitely participate in free radical mechanism reactions. Okay, here light or heat is being utilized, correct? So that the alkane converts into alkyl halide. Okay, so that the alkyne converts into alkyl halide. Got it? It all happens with a reagent that you use. For example, chlorine is the starting material. So we take chlorine and heat it in the presence of light, heat it or use sunlight or UV light. By that, chlorine molecule will convert into radicals, and radicals are usually unstable neutral species. And of course, in the first step, because heat is being utilized, the reaction type is endothermic. So this is an endothermic reaction, the first step, which is also called as initiation. The second step is called chain propagation. Chain propagation is one radical trying to generate a new radical. So you can notice that Cl dot reacts with methane, converts into CH3 dot and HCl. That means the Cl dot will pull H dot from here and release CH3 dot. So this is the methyl radical here. Now, methyl radical will again react with the chlorine present in the gaseous mixture, and it can pull one chlorine and leave one chlorine as a radical. Okay. Now, at any point of time, you will not notice H radical is being released into the atmosphere, released into the reaction conditions, because creating H dot is extremely unstable. So any other form is possible, but H dot radical is not possible easily in gaseous medium. Hence, you cannot create this, but you can create Cl dot, CH3 dot, or any other radical form. So again, this Cl dot reacts with CH4, converts into CH3 dot HCl. I think you got a rhythm of it. So it will keep on converting into methyl chloride most of the time. So within the chain propagation, you will realize a large quantity of methyl chloride is formed. This is step. Step 3 is about after a certain amount of CH3Cl, what happens here is you will see the amount of radicals will start increasing. The concentration of radicals will increase. Suddenly, you will notice that all the radicals will start, attracting each other and try to neutralize themselves into molecules like this. CH3, CH3, ClCH3 will convert into this. ClCl dot, CH3, CH3 dot will convert into this. But the quantity that you will get as compared to that of methyl chloride is in traces. That means in a very small quantity. A typical free radical mechanism, everybody will always have these three steps. The first step is called initiation. Next one is chain propagation. The third one is chain termination. Okay. So these are typical, steps that has to be followed for any alkane reactions. Everyone clear with this mechanism? Now, what are the challenges in this mechanism? Let's address that first. What about the rate determining step? In the propagation steps, we have X dot and CH4 converting into CH3 and HX. You notice that there are two molecules that we have used on the reactant side and two molecules formed on the product side. So hardly there is any change in entropy. And because HX is forming, HX bond is relatively stable bond, so there is always energy released in this case. So delta G, the progressiveness of this reaction mainly depends upon delta H, because this factor is anyway zero, correct? So if this is negative, that means it is exothermic, then the reaction is more spontaneous. Got it? So these two reactions depend upon the both cases, that these two are exothermic or not, or whether the overall reaction of these two is exothermic or not. Now that's what we need to address here. So delta H1 and delta H2 in the case of fluorine identified to be highly exothermic, so much so that it releases huge amount of energy. In fact, if you notice that an average energy required to break carbon-carbon bond is around 40 kilocalories. Now it is releasing 110 kilocalories. That means every carbon-carbon bond will also break if at all you react that with fluoride radical. That's why fluoride radical makes a highly explosive reaction. In the case of chlorine, the first set of reaction is slightly endothermic, but second is highly exothermic. Overall, it is exothermic. So it is still explosive kind, but not something which you can break carbon-carbon bond. Next, bromine overall releases slight amount of energy, which means it is less energy released, which means the reaction is very reasonably happening here. And iodine, on the other hand, overall reaction is positive, delta H is positive. That means it is non-spontaneous. So that means the reaction will go in the backward direction. The formation of methyl iodide is less possible. Okay. So if I put the overall reactivity of the halogens, F2 definitely is the highest, then Cl2, Br2, then I2. This is how the free radical mechanism works. Okay. I guess these points are clear, everybody. Now, you can see In the case of methane, we identified that it is reversible because delta H is positive. But there is one thing we can do. We use some oxidizing agents here, like HNO3, HGO, HiO3. These are good oxidizing agents. And these oxidizing agents, when you react with Hi here, the product which is formed, it will again convert into I2. So if I2 concentration increases and Hi concentration decreases, what does Lee-Shatler's principle says? According to Lee-Shatler's principle, reactant is increasing, product is decreasing is a sign for reaction going in the forward direction. Hence, the reaction will start moving in the forward direction. So yes, this reaction can be made more into the forward direction using mild oxidizing agents like these three. Okay, next. If it comes to alkanes, like if you take N-propane for instance here, react with F2. In case of F2, you notice that the primary halogen is found to be almost 80%. Secondary fluoride is found to be around 20%. And this is because of high reactivity of fluorine. It's very difficult to control radicals, fluorine radicals. So it will be wherever it is exposed to the corners here, correct, it will immediately connect onto that. That's why the percentage on the primary position is increased. Chlorine to some extent is also very similar to that of fluorine. That means it is still more reactive, but it is less selective in nature. While in the case of bromine, if you notice, bromine, when you react, and first position, you will have bromine, but in a very, very small quantity. Bromine will form in a substituted position to a very, very large quantity. Hence, bromine is referred to be highly selective radical and very less reactive radical. Okay. And if you may recall from GOC, we learned that the radical stability is like this: 3 degree, then 2 degree, then 1 degree, then methyl. Hence, bromine will always prefer a 3 degree radical to get substituted more than 2 degree, 1 degree, or methyl radical. In fact, if you compare the rate of substitution on 1 degree, 2 degree, and 3 degree positions of carbon, chlorine's rate at 1 degree, if it is 1, the ratio with respect to 2 degrees 3.8, with respect to 3 degree, it is 5. But in the case of bromine, if it is at 1 degree, the ratio is x units. 2 degree, it is 82x. At 3 degree, it is 1600x. So you can imagine its ability to attack on the 3 degree position is extremely high. Okay. Clear, everybody? So its ability to attack on the 3 degree position is extremely high here. Clear? I guess this part is clear to everybody. Written it again and again. So I'll remove this part. Yeah. Now, what you got to do here, let me show you with one simple question and then we can do it multiple questions here. So check out. Suppose if at all I have, let's say, carbons like this, total how many we have? 1, 2, 3, 4, 5. Now notice if a halogen is exercised to make a substitution reaction here, what are the chances? I can get three types of halogens, one X here, one X here, one X here. These are the three structural isomers we can get. Now the same logic applies for chlorine and bromine also. I can get three of them. Now I need to find out, in case if it is chlorine being used, Cl2 and H nu, and in case if it is Br2 and H nu, what is the percentage amount of this and this you will get. So let's notice that the first case, if you notice, it is a 1 degree carbon. And 1 degree carbon, how much is the number of hydrogens we have? There are 6 such hydrogens we have. So how do we need to find the percentage here is like this. 6 times of 1, because the rate is 1 here, divided by, 6 times of 1 plus how many 2 degree we have? 2, 2 and 2. These two are 2 degree. So 6 times of chlorine, what is the percentage we have? 3.8. This into 100, that would become its percentage amount. Clear? Similarly, notice in the second case. Second case, we have this and this position are same. So these two are similar kind. So how many total hydrogens we have? Four such hydrogens into 3.8 divided by the bottom part is the same because this is the total amount of rate that it can offer. 3 6 into 3.8 into 100. Last here, there are only two of a kind. These are two of a kind. So 2 into 3.8 into 100 divided by, 6 plus, sorry, 6 into 1. Here, 6 into 1 plus 6 into 3.8. While in the case of bromine, everybody, the first will be 6 into 1 divided by 6 into 1 plus 6 into how much is the amount? 82 into 100. Now here 4 into 82 into 100 divided by 6 into 1 plus 6 into 82. That is a percentage in the second case. Now here 2 into 2 into 82 into 100 divided by 6 into 1 plus 6 into 82. So this is the percentages you can see. Now, based on the numerator, you can notice that between 1, 2, 3, in the case of chlorine, this is the highest. In bromine also, this is the highest. So, whether it is bromination or chlorination, in both cases, this is major. This is major amount. Everybody, please do check. I hope you understood how to figure out and calculate the percentage content of different positions of halogens. Clear about that? If you understood that, please notice this next reaction also. In a similar way, I have done the same thing with chlorines. Please notice that you get 64% on the primary and 36% on the tertiary position. Next one. In the case of bromine, you will get 99.5 percentage. Same thing. If you notice, you will get 99.5 percentage. Okay, on the tertiary, even though there is only one hydrogen, you will get 99.5 percentage. But primary position, you will get only 0.5 percentage. Now, usually a radical, if you recall from GOC, we learned a radical is sp2 hybridized carbon. That means the other three groups which are present along with it will be planar and they all lie on the same plane of this carbon. So which means the lobe above and below is exposed for the reactions. So imagine when the bromine comes and make a reaction with it. So radical will connect either on the top lobe or on the bottom lobe. The chances of connecting from the top lobe or from the bottom lobe is 50-50 percentage. So if it is 50-50 percentage, can I say that I can get a dextro form of 50 percentage? I can get a levo form of 50 percentage in case if this carbon is a chiral center. And if I get both 50-50 percentage, what do we call it? We call it as racemic mixture. We call this as racemic mixture. Yes, everybody. So this is what we learned earlier as well. What is racemic mixture? How to identify dextro levo in that. So you can see here we can get racemic mixture. This is a very standard question that will be usually asked to you. So please do check. How many substituted product, including stereo, are possible on monochlorination? Okay, if you have monochlorination, how many are possible? See, on this position, I can have one chlorine. Here I can have one chlorine. Here I can have one chlorine, and here I can have one chlorine. But that makes this as a chiral center. Here there are two chiral centers, and two chiral centers. Total, including stereo, we have 10 such isomers. And second, how much is the percentage chlorination and bromination is found in the following? Correct. So percentage chlorination, you can notice that on A position, we have this is the percentage amount. I want all of you to just go through it once and check and do the same thing, same calculation for bromine. For bromine, what is the amount for 1 is to 2 is to 3 degrees? We have rate as 1 degree, 2 degree, 3 degree. Rate is 1 is to 82 is to 1600. I want you to watch it for chlorine and work out the same thing for bromine. Please work out the same thing for bromine and give me an answer, everybody, how much you are getting in the case of bromine. Yeah. In case of alkanes, the first type of reaction is halogenation, and halogenation is a free radical mechanism. Let me give you the synopsis quickly, orally. First, rate determining step is determined on the basis of chain progression steps. Okay, chain propagation steps. In case of fluorine, it is highly explosive. In case of chlorine, it is still explosive. For bromine, it is very selective. For iodine, it is reversible. Iodine can be enhanced into forward direction using mild oxidizing agents like HNO3, HiO3, or HGO. Third case, we learned that the rate ratio at which the halogen can attack on primary position, secondary position, and tertiary position, specifically in the case of chlorine and bromine, are being um, uh, experimentally identified. And that is for chlorine, it is 1 is to 3.8 is to 5. For bromine, it is 1 is to 82 is to 1600. All good? Right. This is the synopsis of the first reaction. Next, go to the second reaction. Okay. Now, the second reaction is here. I'll go up again and explain. Check out. The second reaction is called aromatization. That is, there are certain reagents, in fact, some metal surfaces which are oxide based. So Al2O3 metal surface, Cr2O3 metal surface, if you mix both of them, convert into small, cylindrical forms like pipes, like small pipes, and heat those pipes strongly and send the uh, alkane gases into it. Okay, specifically starting from hexane onwards. So if N-hexane is passed through those small tubes, which are made up of Cr2O3, Al2O3 at very high temperature, as good as 500 degrees, and pressure of around 10 to 20 atm, then the hexane part will convert into benzene and rest will convert into H2. Okay, so H2 gas and benzene. So the minute benzene is formed here, we call the reaction is aromatization. If you send N-heptane, you will get the methyl getting substituted on benzene, and you will report the answer as toluene. Okay. If you take N-octane, you will notice first a benzene is formed, rest of the methyl radicals will attack on ortho position, meta position, or para position. See, two methyl groups on benzene are called as xylenes. So we will get orthoxylene, metaxylene, and paraxylene as major products. And along with that, you can also have an ethyl directly connected to benzene. So overall, you will get four products, and usually these three are major ones. Okay. The alternative reagents to Cr2O3 and Al2O3 includes V2O5, molybdenum oxide, correct, or Fe2O3 and Cr2O3 mixture. These all have similar roles. They will make these alkane groups into aromatization. Now, since the topic is about alkanes, we are specifically sticking to alkanes. Otherwise, this is what I have written. In case if it is cycloalkene and cyclodiene like this, if you already have a cyclic structure, then you pass it over sulfur and then heat it, selenium and heat, polonium and heat, platinum, palladium and heat. They will also convert into benzene form. So this is also an alternative aromatization reaction. All good. This is called aromatization reaction. No mechanism for it, everybody. Here, mainly, you need to remember that this six-membered ring, seven-membered ring, eight-membered ring will convert into benzene forms. Next, pyrolysis or cracking. Pyrolysis or cracking means you are breaking the carbon-carbon bond and carbon-hydrogen bond to convert into smaller molecules. Suppose if methane is pyrolyzed at around 100,000 degrees, it can convert into coke form, right? Carbon coke and H2 gas. If it is about ethane, it will convert into ethene plus H2. If it is propane, it can convert into propene, ethene, methane, and some amount of H2 as well. These are the forms which you can get. Next, this is called pyrolysis or cracking reaction. Next one is isomerization reaction. And notice, in case if you have N-butane and I react with AlCl3 and HCl at around 200 degrees Celsius, okay, this will undergo, you know, uh, branching of the alkyl groups. That means a methyl will break at one end and that same methyl will connect on the other end, making it into a branch form. Usually, this reaction is specifically done to increase the branching. For example, I have isopentane, one, two, three, four, five, sorry, isohexane here, total six carbons, so isohexane. So in that case, if you react with AlCl3 HCl, this should be anhydrous by the way, it is not anything aqueous at all. These are all in anhydrous form and in gaseous state. And that on heating, what it will do, it will break this bond here and convert into this form with a branch. That means that will come here. Or it can come at this position also. Like this, the branching can happen. Now, usually, I mean, this is a suspected mechanism, everybody. It is not an appropriate mechanism. This is one thing which was claimed by Morrison and Boyd. Morrison Boyd is a book which is a standard book used. In that, they claimed like this that there is a small amount of propene that is used for making this reaction. A propene will take H plus from HCl, convert into a carbocation. Okay. Now, this carbocation will take H minus from these positions and convert that into carbocation of the substituent here. So N-butane is what I took originally. So that will become N-butyl carbocation. And in this carbocation, what would happen? Here, at this position, the carbocation, what it will take here, this carbocation will rearrange onto this primary position. And then you will notice that this hydrogen will shift again here, making this methyl shift to happen. What does that mean? See, here positive charge is there. From here, imagine this methyl is breaking and methyl is coming here. If it comes here, positive charge will erupt at this point. And this is an extremely slow process. That's why it is the rate determining step as well. And once you get a positive charge here, from the original propene, which has converted into an, where is it? Propane here, because it took the H plus from here and converted itself into a propane form like this. So that propane's hydrogen will be fetched back by this positive charge and leave behind the propene again. So the propene was taken as a catalytic amount, small amount that will come out. And hence the branching is happening. But if you ask me, sir, is it a appropriate mechanism? I would say little exaggerated, not well-defined mechanism. But this is the only available mechanism we have, which a book can, which standard books are offering. Clear? But honestly, mechanism is not something which you have to worry about in this reaction. You just need to focus on the branching part. So remember, the terminal methyl groups can come across and start increasing the branching. That's the whole point of this reaction. Okay. This reaction only happens specifically on the alkyl part of the molecule. Okay. Fifth reaction is oxidation reaction. See, if you take methane, react with O2, that means oxidation. But this time in the presence of red hot copper tube or red hot iron tube. RHIT means red hot iron tube with high pressure and high temperature. Or I can take copper, written as 523 kelvins and 100 atm pressure. Yeah, take small copper pipes in that, fuse methane and O2 and heat it strongly. That methane will convert it into methanol. This is an industrial reaction, no mechanism defined. So remember directly the product form. Instead of copper, if I take molybdenum trioxide here, then it will convert into a formaldehyde. And if I take manganic acetate salts and then you heat any alkane, that alkane will convert into acids. So here it should have been R, sorry, it should have been R, RCOOH. NCRT has given this reaction, that is CH4 plus O2 in the presence of MnOAC twice. It will convert into HCOOH plus H2O. Got it? This is the reaction that has been given. The next one being, tert butane. This is tertiary butane. Tertiary butane, when you treat with KMNO4, okay, KMNO4 in a basic medium is a strong oxidizing agent. It can pull over this hydrogen and insert oxygen into it, thus giving a 3-degree alcohol. Okay. Now these are directly taken from NCRT. They are only industrially observed, so no significant mechanism available for it. And notice this reaction is one of the favorites asked in JEE mains. So that is something which you need to remember, this 3-degree formation using KMNO4. Hmm? The next reaction is nitration. It is also a free radical mechanism, everybody. There, if you notice, HNO3 will first convert into this HO and NO2 dot radical. Okay. And in the ethane, when you react with concentrated HNO3 and heat it strongly, this NO2 radical will go and attach onto this carbon. And it can attach like this. Here also, when this mechanism happens, the energy released is sufficient to break carbon-carbon bond. It is explosive reaction. That's why this is not the only product you will notice. After carbon-carbon is broken, a CH3 dot will also form. That will also connect to NO2 and get this CH3NO2. So you will get ethyl nitrate, ethyl nitroethane. You can also get nitromethane. In case if you have propane, you will get, nitropropane, you will get isonitropropane, you will get nitroethane, you will also get nitromethane. All the products are possible in this case. Again, this is also very favorite JEE question. Again, taken straight from NCRT, that how many number of products you will get. Okay, this is again been a very standard JEE question. So all you need to do is keep cutting the number of carbons. Every time you cut, you make it into a nitro group. That's it. Okay. Next, sulfonation. If you compare H2SO4, that will convert into HO dot and SO3H dot. And if you have propane with fuming H2SO4, SO3H will connect at primary position or secondary position as per the given form. Now, SO3H behaves similar to Br dot. That means it is, highly selective and slow reaction. Slow reaction. Therefore, it would also have a similar rate as that of bromine. So that's why it will offer major product on more substituted position. And here also, it will not provide sufficient energy to break carbon-carbon bond. Hence, you will get only without carbon breaking, Wherever you can substitute them. Those are the products you can get. Alternatively, if you compare the reactivity, you will see 3 is greater than 2 1 and methyl radical. This is the reactivity what you will observe. Correct? Usually this reaction is observed for carbon 3 and above chains. Okay, 3, 4, 5, 6, and so on. Got it? So these are the reaction types of alkanes, everybody. Correct? In the case of alkanes, there are two parts that you need to learn. One is how the chemical reactions, how is the chemical reactions. The next one is about preparations of alkanes.